So all of our variance and standard deviation discussions are based off of using the mean as our idea of center. If we use our median as our idea of center, then we can't use standard deviation. So I'm right away in a position where I have to change my idea of how we measure spread because both variance and standard deviation require we subtract the mean from the data values. I don't have a mean, I only have the median. But finding the median requires us to deal with the list in order in the first place. So I'm going to use the left side as the low side, the right side is the high side. And I've got my list put in order and chunk right in the middle, that's our median. So what I can really think of is that I've divided our list into two categories, the low half and the high half. But what if I chose more categories? And now you have a decision as to how many parts you want to divide your list into. And depending on how many parts you use, we'll call it something different. If we use 100 parts, we'll call them percentiles. If we divide it into 10 parts, we'll call them deciles. 5 parts would be quintiles. And 4 parts would be quartiles. Now, depending on your application, one of these may be better or worse, more useful or less useful. Percentiles show up in standardized measurements frequently. A bunch of percentiles are used for benchmarking behavior. So frequently we'll talk about like the 95th percentile, high end, the 5th percentile on the low end, the 10th percentile. And in that case, we've divided our entire data set into 100 spots. This really is only beneficial if I have large data sets. My JD Power data set only has 33 pieces in it. Doesn't make sense to divide that into 100 bins. Some of those bins will be empty. Deciles show up frequently when discussing things like standardized test results. Bureau of Labor and Statistics tended to use quartiles a lot. Employment statistics tend to use quartiles a lot. So I'm going to focus on those, but the idea is the same. I have to figure out where my bits are. Questions? If I give you a list of numbers, how do we figure out where the quartiles are? My list has to be in order. All right, well, let's think about this. I'm dividing it into 4 equal sized groups. Well, I divide it in half, and then I take each half and divide that in half. So this is almost a recursive process. I'm going to find the median. And then the quartile 1, the dividing line between the first and the second quarter, will be the median of the low half. So this finds the median, which I'll call Q2, because it divides the second and third pieces. The median of each half, Q1, is the median of the low half, and Q3 is the median for the high half. So this is basically finding the median and then finding the medians again. But if I remember correctly, finding the median depended on how many numbers were in our list. It is possible that if I give you a list, the median might not be one of the numbers. I picked a very small list on purpose. What's the median of this list? What was that, Max? I thought you had it right. Right, because the median is the halfway point, but since I have 4 numbers, the halfway point should be between 2 of them. So the median is the average of those 2. But if I were to give you a list like this, with an odd number of entries, then the median is one of my values. It's right in the middle, low half and high half. But now, this side, I need the median there to find the first quartile. This side, I need the median there to find the first quartile. Again, I have an even number of things, yes? So over here, what's Q1? Again, it's a dividing line. And the third quartile so in spite of the fact that I have a very small list, none of my quartiles are actually on my list. In the odd side, I have a choice to make. So over here, I have a different question. Is Q2 part of either half? This is a decision you get to make. Some people would say, okay, well, then the low half is the numbers 1, 3, and 5. And the high half is the numbers 5, 7, and 9. You include it in both of them. Some people say, no. That's the dividing line itself. The low half is just 1 and 3. The high half is just 7 and 9. So we have to decide, are we doing inclusive or exclusive quartiles? Nope, we're still here. Now, that actually would even go so far as to make a difference in my even group except for the fact that the quartile wasn't one of my numbers. And I don't want to include a number I made up as part of the list of data to find the other things. So this really only comes to be a difference when I'm looking at lists that have odd numbers of entries. So in here, in this list, 13579, there'll be two different versions. If I'm doing it inclusively, what's quartile 1? Now that's the list. That's the half I'm using. To find the actual quartile, I need the median of that list. So the median of that list would be 3. And then when I go up here to do the third quartile, the median of that list would be 7. But if I do this exclusively, well, then my low list is just 1 and 3. And my quartile is 2. And my high list is 7 and 9. My quartile is 8. You can choose which one to do. Match one, question? Sir? Okay. Please note that in Excel, where's my JD Power data? Here it is. Share. JD Power. So here's that list of number of defects per 100 vehicles. Over here, I've got the quartiles. I've got a lot more, but I've got the quartiles. I just asked Excel to generate a quartile. But notice the command to get Q3 says quartile.exc. That's the exclusive version. So it doesn't include the median as part of the high half. And notice it says comma 3. The comma 3 wants the third quartile. If I want the median, I can give the same command. I can give quartile exclusive comma 2. I can also give the command median like we did on Wednesday, but I can do it either way. Quartile 1. Low is just minimum rather than, but you could use quartile 0, and maximum you could use quartile 4. If I change that .exc to .inc, then I'm doing the inclusive versions. Only difference is which number it chooses, whether or not we've included that median 185 in the lower high half. There were 33 numbers here. If I take the middle one out, there are 16 in the high and 16 in the low, and that means that in the exclusive version, quartile 1 and quartile 3 are between values. We have an even number. If I do an inclusive, quartile 1 and 3 are actual values themselves. Page 124, here, I have a picture based on how many things are in my list. And notice in this bottom version, there are enough data values for the quartiles to all be data values. There's an odd number, and when I do the exclusive version, there's an odd number below and an odd number above. In this third line, there's an even number of data points. So my median is between, but then the low half is 5 and the high half is 5. So quartile 1 and 3 are actual values. It literally is your call whether to do inclusive or exclusive. Inclusive will raise quartile 1. It will lower quartile 3 ever so slightly, because we've added one more data point and brought things in slightly. This repeated median behavior is called the method of medians for determining quartiles. I've never heard it called that outside this book, but it is mentioned as the method of medians right here. Questions? Missed it, or did I put it? There it is. Sometimes we want to know the relative sizes of the quartiles. So we look at things like the interquartile range, which is how far it is from Q1 to Q3. That's the middle 50% of your data. So we tend to think of that as the center piece, and then the outsides, the first quarter and the top quarter, as the edges, the middle versus the edges. And then we'd say, well, is this data spread out? Is quartile 4 much bigger than quartile 3? Is quartile 1 much bigger than quartile 2? So we can visualize this. Again, going back to that J.D. Power example, in addition to having the medians here, I have this box plot. What the hell is this? A box plot is literally just the 5 numbers we get from our quartile examination. The low, quartile 1, 2, 3, and the high. So that's these 5 numbers over here. And that's these 5 horizontal marks. So I have the low, first quartile, the second quartile, third quartile, and the fourth quartile. So I can see the interquartile range, it's the size of that box, from top to bottom. I can see that clearly the fourth quartile, that top section, is much larger than the first quartile. This would give rise to me saying this data is skewed right, because there are much more pieces at the high side than there are at the low side that are further out. This is often called a box and whisker plot. I hope it's obvious why. Which means if I want to put one in, box and whisker is available under my histogram, under insert chart. Okay. Questions? There are some other things in here. I have percentiles here. And I did percentiles using Excel. Again, the same idea, inclusive versus exclusive. They're both available, right? Please notice there's a problem here. Inclusive and exclusive percentile. How do you figure out what percentile something is? I only have 33 numbers here. How can I find the 30th percentile if there are only 33 numbers? I need a way to figure out where in my list I should be. So the way we calculate what percentile we have, I'll come back to this in a moment. What? Yeah. P. The Pth percentile is found by going to the K equals P over 100 times N plus P over 100 spot. Sure it is. What the does this mean? If I want the 15th percentile, I take 15 over 100 and multiply by, how many things were in my list? 33. But that's going to give me a decimal, right? It's going to be between numbers. So I round up to the next number in my list. This guarantees me that I've got 15% of my numbers under that spot. Or if I did the 60th percentile, I'd be having 60% of the numbers under whichever place we came up with. If my data set is smaller than 100 numbers, this is guaranteed to be between things. That's okay. If my data set is bigger than 100 numbers, I could still be between things. Let's go back to that JD Power set and take a look at what I actually did in Excel to do those calculations so I can show you what happens there. Here, the C column are the actual numbers for defects. So I went to the 90th percentile. And I said, find me 0.9 times 33. Grab your calculator. 0.9 times 33. See, 29.7. Find me the 29.7th thing on my list. That's guaranteed to be between numbers, isn't it? So it goes between the 29th and the 30th, and it interpolates. It tries to draw a straight line between those data values and move 9/10 of the way along it. The plus P over 100 on the end, right? So it just adjusts the list. I actually said, hey, let's do the 90th percentile of the A list. The A list is just the numbers from 1 to 33. You came up with 29.7, didn't you? And then we added 0.9. So it went between the 30th and the 31st number. I guarantee you that they're down there, right? I don't like this. When my lists are small, these boxes don't make the same intuitive sense to me that the quartiles make. I know where they are. Percentiles are a little rough. Now, if I do the inclusive version, it was out of 32, not 33. So it changes stuff around, right? It rounds it differently. I hate this. I hate this. But that's also why this one is a 0. I want a number on your list that is bigger than 100% of the data. Oh, and you're not allowed to use the top number. Well, then that's not a number on my list, is it? If you are allowed to use the number, well, then it is the top number. That's the inclusive percentile. That to me makes more sense. In smaller data sets, this is annoying. I don't have a good way around it. This is why Bureau of Labor and Statistics uses percentiles, because they're dealing with millions of data points. And then putting stuff into 100 boxes makes it a little more intelligent. If I've only got 33, I wouldn't bother using such a large number of containers. Questions? It's kind of hard to see on the screen here, but in the middle of the box is an X. It's very, very faint, unfortunately, because of the color there. Let me change the color. Format data series, paint, fill, no fill. Will it work? Ha! There it is. It's empty. See the X? The X is the average. The average is a little bit higher than the mean, right? Sorry, the median. The median is the second quartile, the middle horizontal line there. The X is above that. This again lines up with my idea of being skewed, doesn't it? In addition, I have these two things labeled fences and this thing labeled the mid-hinge. The hell? Okay. We talked about outliers, right? What was an outlier in terms of mean and standard deviation? Talked about it in z-scores. So either above the third standard deviation or below the third below, right? So +3 or -3. When I look at the interquartile range tells me the top to bottom of the box. So I say, well, let's go up that far and half again. So we'll take the interquartile range and we'll multiply by 1.5. And we'll go from the median that far down, and we'll go from the median that far up. And we'll make fences there. And that's what I call them, the high fence and the low fence. Those are the edges that are 1.5 times the interquartile range. That's my definition of outlier for this kind of data. Now, in this case, the lowest piece of data is 139. So nothing is outside the low fence. There are no outliers in that direction. The high fence, well, the biggest number is 265. If I use the exclusive version, nothing's above the high fence. If I use the inclusive version, there are a couple of data points above that high fence. So there are a couple of outliers in this version of fence. There's one other number here called the mid-hinge. The mid-hinge is the average of the first and third quartile. Q1 plus Q3 divided by 2. There is no automatic calculation for that in Excel. I wish there was, but there really isn't. And as far as I can tell, I've not seen any reports ever use the mid-hinge as an important piece of data. So while it's mentioned in the textbook, literally I've seen no one use it. But again, this is a less sensitive measure of center because it's not influenced by outliers, it's only influenced by the quartiles. Questions? So I got a lot of math I can do with mean and standard deviation. I have a little less I can do with quartile percentile work, but it requires me to have this different perspective on where things are. Close that. By the way, here I did the 13579 setup. You see the inclusive versus the exclusive. There used to be a quartile command that didn't have either of them. If you don't write inclusive or exclusive, it defaults to the inclusive one. Okay. Let me get rid of that file for a little bit. And remember that JD Power file is on our Canvas page along with any Excel file I've shown you today that I've worked through or all week. They're in the examples for class section. The other piece we do frequently is we look at relations between data sets. Remember our scatter plot, right? So the stock price one on the homework. So if I pull up a scatter plot, here, I've got a scatter plot. This is problem number 53, and it shows the original set of data. Shows the square footage of a house versus its selling price in thousands of dollars. So I would ask the question, are bigger houses more expensive? Do you think so or not? Okay, let's see. I'm going to create a scatter plot out of this data. Highlight both columns. Insert. There's my scatter plot. Bing. There we go. I have a scatter plot with all of my data on it. Square footage across the bottom, price up the side. Well, is this a strong relationship? A weak relationship? I don't know. On that homework question about the stock prices, we would look at this and we would say, all right, is this data grouped closely together or spread out? What do you think? Looks closer. So I would expect this to be a stronger rather than weaker relationship. Is it a positive relationship or a negative relationship? Because both numbers go up at the same time. As my size goes up, my price goes up. Okay. Variance. Let me think about spread, right? If these data were in perfect line with one another, I would say that they vary together. Perfect. But they don't vary together perfectly. I have two houses here that are about the same selling price, but are fairly different in size. I have two houses here that are almost exactly the same size and very different selling prices. So they aren't quite varying perfectly together. What we instead can talk about is the covariance, how they vary relative to each other. Unfortunately, the way to measure covariance is atrocious. The formula for covariance is disgusting. Where is that? That is on page 133. Covariance. I'll come back to you. Blah. The hell is going on here? Oh, wait a minute. Covariance is based on mean, and we're doing something like a standard deviation. I have the mean for the x values, I have the mean for the y values. I take the difference, that's the deviation, and multiply the x deviation and the y deviation together. And then I add all those up. Oh. I'm never going to use this directly. But what I can say is that if this number is big, then I've got a large spread. And if this number is small, I've got a narrow spread. In terms of how the data go together, around some idealized middle, are they spread out a lot or they just spread out a little? This is very much similar to a standard deviation. That's why we give it that sigma or S, just like we did with the standard deviation, only this time we need to label which one it is. It's the covariance, so it gets both letters, X and Y together. Problem is units here. Because I'm multiplying variation in X and variation in Y, this would be dollars times square feet. Not dollars per square foot, but dollars times square foot. That doesn't make a damn bit of sense. So I would rather rearrange this and do some extra calculations and take this in terms of standard deviations. So let's go back to our standard deviation idea. And instead of looking at this covariance, let's look at something we call correlation. Correlation. I've heard that word before. What did we talk about correlation before? On our scatter plot, we had this idea of correlation. And we said that if the numbers were close together, we had a strong positive relationship, we'd have a correlation. Aha, here we go. If I have a strong, close together piece, those should be highly correlated. If I have a strong, close together piece, those should be highly correlated. These are a little more spread out, they'll be less highly correlated. These don't actually seem to have any relationship to one another. These are tightly gathered, but there's no up, there's no down. So these have correlations very close to zero. But again, disgusting formula. There's my correlation. No, I'm never going to make you do this by hand, ever. Excel will do it. Graphing calculators will do it. Every piece of statistical software on the face of the planet will do this. This is called the Pearson correlation coefficient, or the sample correlation coefficient. And it turns out that this number is always between -1 and 1. The reason it's between -1 and 1 is technically it's the cosine of an angle. And in trig, years and years and years ago, I remember, cosine is always between -1 and 1. This is an angle, well, related to an angle. That's a very weird concept to think about data as angles. I promise there's something to that. It has to do with a linear algebra idea. We'll skip that for now, but it's always between -1 and 1. The closer we are to 1, the more positive and tight our relationship is. The closer we are to -1, the more negative but tight our relationship is. So we're looking for numbers that are close to 1 or -1 to tell me I've got a strong relationship here. But even if I have what looks like a weak relationship, I can calculate the correlation directly. Let me go back to my share. I would like the correlation here. So in order to get this correlation, I'm going to go over here and I'm going to say, I want correl. Hey, correlation. Of what? Well, it asked me for two different sets of numbers. So here's the first set, comma, here's the second set. Close my parentheses, enter. Pretty close to 1, yes? That tells me that this is a strong correlation between these two. More expensive homes are larger. Larger homes are more expensive, whichever way you want to phrase it. They go together. What I could do is ask, this was a measure of spread, right? It's a spread around something. What's it around? There should be some sort of line here that says, oh, every time you go up in square footage, this is how much your cost goes up. How do these correlate? What's the correlation? What does it actually do? Well, I can actually ask Excel to generate that line. It's called a trend line. And if I right-click on one of the data points and I say, aha, there's an add trend line button. Click. There's a dotted line on the picture now, isn't there? Now I can see the spread above and below that line. And we're tightly clustered to that line. This is a strong correlation. Goes with my nice correlation coefficient there. I should actually write that right there. Now, if I'm on that line, let me re-highlight that line. Click. See how it's got all this garbage over here? we've created a linear trend. The computer is smart and can do a lot of other types of correlation graphs, trends. It can do exponentials, logarithms, polynomials, power functions, x to some power, walking averages. There are all sorts of things I can do. But I can go a step further and I can ask it to give me more information down here at the bottom. Display equation on chart. Display R squared value on chart. Take that 0.83, whatever that is, square that. What do you get? .6952. If I ask it to also give me the equation, what does that mean? What's that equation tell me? Good, that's a line, so it's got a slope and it's got an intercept. But what do those mean in this setting? This is now the interpretation job. I let it do all the work. What do those things mean? That slope, 0.2092. It's a slope. Slope is change in y over change in x. So something per something. What are our y units? Almost. It is dollars, but it's thousands of dollars. And our x? Square feet. So that says for every change in square footage of 1 square foot, your value should go up $0.2092 thousand. So every additional square foot of the size of your house gains you $200. 0.2 thousandths, right? Now, that's 74.29. The heck is that? A y-intercept. But a y-intercept would be way back here on the graph, right? So a house of 0 square feet should still cost $74,000. That makes sense. Not really. I don't think you would ever sell a house and say, hey, this has 0 square feet to it, come by. Well, we could say maybe that's the lot price. Maybe that's just how much the land itself costs. So the question now becomes, can we interpret these numbers in terms of our problem situation here? In terms of what these numbers mean in this setting? Can we figure that? Questions? Correlation coefficient R is really only useful for linear relationships. In spite of the fact that I have all these other relationships up here, I really don't have a good idea of how R matches these other things, except to say it's how tightly around the picture we are. R values are specific to straight line graphs. It doesn't make much sense to do R for these other pictures. And as a matter of fact, there's a really nice, where did I put that? Really nice picture. Please open properly. You're not going to open properly. Let's open it in Word. I thought you'd appreciate this. All of those bottom scatter plots all have a correlation coefficient of 0. You can still see some really clear patterns, can't you? But they're all 0 correlation. Come on. Correlation really only matters when we're dealing with lines. and grouping around lines. One other piece. If I am dealing with grouped data, like we did with our frequency histograms, right? Grouped data. So I would have ranges. What if I asked you to find the average for this set of data? I have a problem, don't I? I don't have the actual data in front of me. I just have this summary. How can I find the average? I might not be able to find an exact average, but I can at least approximate it. By saying I'm going to make believe that the data for this first bin is in the middle of that bin. If I'm looking at numbers between 2 and 6, what's the middle? We'll write that down as like the median, right? The median here is 4. What's the median here? Between 6 and 10? And now I will say, okay, so I really have frequency times median. 7 times 4 is 28. 12 times 8 is 96. 3 times 2 is 36. 2 times 16 is 32. And 1 times 20. Now add all of those up. That's, I've already done it. I'm just reading off my own paper. That's 212. That's going to be my total. How many data values do I have? Well, add up the frequencies. And I have 1925 of these. So my average is roughly 212 over 25. When I'm dealing with grouped data, this is a perfectly legitimate method. By the way, now that I have a mean, I could do a standard deviation, couldn't I? I take each data value minus the average, square it, multiply by how many there are. Take a look at the example on page 137. Our range, frequency, median. Here's our calculation of our average. Here's our deviation, our standard deviation, when we multiply by how many there are. This intermediate extra calculation is, again, automated in Excel. I'm not going to ask you to do this by hand. But then to use this the same way, we used mean and standard deviation before. Questions? This ends chapter 4. That means our homework for chapter 4 is due on Wednesday. That also is a good place to have a first exam. And that means that the first exam will be Friday. There is a about the first exam on our Canvas page. I don't have a review sheet. I just have this about the exam. I will tell you more about the exam on Monday. So if you have questions between now and Wednesday, come bug me. We'll see you all then.